So that should be correct. The recording has started. Okay, so thank you everyone for joining our seminar series today, which is Advancing Predictive Models and Decision Support System for Avian Influenza Control. Today we have two presenters, Dr. Lene Kjær from Denmark and Dr. José González from Wageningen Research Institute. The seminar today is being hosted by Poultry Health Research Network and by AI for Food. As a note, if you have any questions, please put your questions in the chat. And at the end of today's seminar, we will have a discussion session addressing your questions and also some interesting facts from the presenters. Today's moderator will be Dr. Rosita Dara. Please go ahead, Dr. Dara.
Thank you very much, Nitish. Good morning, good afternoon, everyone. I'm delighted to welcome you to this important conversation again and to introduce a lineup of truly remarkable speakers, internationally renowned scientists who are at the forefront of this field. Their work is shaping the global understanding of avian influenza and guiding the actions we take to manage its risk to animal, human, and ecosystem health. As Nitish pointed out, this webinar series is a joint effort between Poultry Health Network and also AI for Food, Artificial Intelligence for Food. But I just wanted to today to just briefly mention the mandate of AI for Food for those of you who are not familiar with this initiative. We have launched a technology hub called AI for Food, in which we not only look into the applications of applied artificial intelligence in the context of agriculture and food, but also we bring the governance aspect in a kind of integrated manner to this initiative. So many of the use cases, including the avian influenza, which is a topic that I'm currently working on, there are other ag-specific topics that my other colleagues are leading, or maybe food specific. We take a kind of a case study or use case approach in which we tackle the whole problem, which of course involves data, stakeholders who are involved, and the decision makers, and the problem, the modeling problem, with governance kind of embedded in every life cycle phases of data and modeling, the algorithm development. This will ensure privacy of individuals whose data are being collected, and also it ensures that the end users are in the loop, so that the tools that we are building will be useful. So we have brought this approach to avian influenza to a great extent. We have involved many stakeholders in Canada to give us feedback on the decision support system we are building or other decision support tools that we are building. So if there is an interest, we are looking for to expand our collaboration. With that, because I haven't had a chance to speak about AI for Food in the previous sessions, and probably won't, because I'll pass on to Nitish the remaining webinar series to moderate. With that, I'm going to thank you for joining us. I hope you find the presentations insightful and thought-provoking. We look forward to receiving your questions and feedback, which would be they will be quite valuable. So I'm going to introduce, let me just bring my note up. I had Jose first on my list. Nitish, is that the arrangement?
Sure, yeah, we can do that, yes.
Okay, so maybe I think you had Lene. Okay, so
yes.
Dr. Lene Jung Kjær. Lene is an associate professor in epidemiology at the University of Copenhagen, and her primary focus centers on modeling biological phenomena, including disease transmission, pathogens, and vectors. Her previous work included agent-based modeling of chronic wasting disease and white-tailed deer in Illinois. Machine learning models of tick-borne pathogens and modeling highly pathogenic avian influenza, HPAI, in Europe and Asia. I just want to quickly say that Lene's, one of her recent publications has gained quite a bit of an attention. I have noticed that some of my colleagues are tweeting her recent publication, which shows the impact of her work. So with this, I'm going to welcome Dr. Kjær to start her presentation.
Thank you very much. I am gonna share. Can you all see my slide?
Yes.
Good.
Yeah, that's good.
Right. I am here to talk about some modeling we did in the Enigma project. And for those of you who were here at the webinar on the 30th of April, my colleague Kjær was probably also presenting some work from the Enigma project, which stands for Early Warning System for Avian Influenza. So, of course, we didn't do this alone. We were funded by the Danish Veterinary and Food Administration, as well as the European Partnership of Animal Health and Welfare. And we also work with researchers at the University of Sydney and Statens Serum Institute in Denmark. So first of all, here we have a map of the major global bird migration routes, and Denmark is situated where a lot of different routes meet. So we have a lot of migrating birds. We have a lot of coastal areas and wetland areas. So we were hit pretty hard when the most recent HPAI epidemic started around 2020. And because our department and our avian influenza group are part of the Danish contingency, so we actually advise the Danish Veterinary and Food Administration. We have a need to understand the transmission of HPAI and also for seeing if we can predict the risk for transmission and outbreaks in the near future. So originally, I don't know if Kjær told you about, we had a PhD student called Yang Yu. She has created a very fine scale model for all of Denmark, looking at transmission from wild birds. And this model that we created here was actually just meant to be used as an input to her simulation model. We wanted to be able to predict the timing of outbreaks and detections in Denmark based on what was happening around us. And we wanted to see if we can do it with readily available data from Vejrs. And so we looked into many different modeling techniques, and we discovered this modeling framework by Meyer et al. And thought it looked very, very promising because it's both spatiotemporal, but it also takes into account a transmission both from within a region or a country and between regions or countries. And it furthermore divides into an endemic and an epidemic component. So this, I'm not going to go into the details about the stats behind it and the algorithms, but the expected number of cases in region I at time t is modeled as this equation is showing you, where we have the endemic component, then we had an epidemic within region component and an epidemic between region component. And each of these components are estimated by log linear functions. And so the endemic component, that represents the baseline level of disease that is expected to occur regularly, independent of recent cases. So if cases occur without recent local or neighboring cases, then the model would attribute them to the endemic component. Whereas if cases follow recent spikes in the same or nearby regions, they would be attributed to the epidemic component. And when we look at between region, we could both incorporate short range transmission, which is just neighboring countries, and long range, which is a distance decay function. We also included covariates and seasonal waves, and you can also include offsets in these models. And when we look at the Vejrs data, this is the original model we created was based on data from 2016 to 2022. So in the left map, we can see aggregated data for 2016 to 22 for 37 countries in Europe. And we scaled it per 10,000 square kilometers. And what we can see on this map is that Denmark and the Netherlands, Hungary, and England or Great Britain had quite a lot of cases compared to the size of the countries. If we then look at these number of cases over time, we can look at the right graph. It shows the number of detections per week from this same time frame. So this is actual detection data. And over time, we can see that from 16 to late 2021, we have more or less seasonal patterns in the number of detections, with most happening in the autumn and spring, which of course coincides with migrating birds in Europe. But then from 2021 to 2022, we start seeing detections during the summer as well. So the patterns have changed. So for this model, we actually decided to include the 37 European countries. So we ran the model country-wise, but then we ran a model from the first time period from 2016 to late 2021, and then another model from late 2021 to 2022, because we saw that the temporal pattern had changed. Because this kind of modeling is highly data driven, because of data constraints, then we had to aggregate with H5 subtypes, and also we included both domestic and wild birds combined. And then we looked at the weekly number of detections for each country areas and offsets, and the area of wetlands and the length of coastline were included as covariates. We included seasonal waves, short and long range transmission, and some random elements as well. And we ran multiple combination and tested which model would best describe our data. And those final models were then used to try and forecast. And here to the left, we have the model based on data from 2016 to 2021. Here we are only showing from 20 to 21. This model included long-range transmission. These graphs depict simulation of detection based on the best fitted model for each period. And the solid dot to our left is actual detection data, and then the rest to the right, it's then the model simulating at the amount of detections based on the model parameters. And these are fan plots, so they represent the 1% and 99 quantiles of a total of 500 simulations each week, and the mean is displayed as a white line. And the open circles are actual reported number of detections. So to the left, you can see how, of course, it sometimes over and undershoots with the mean, but it follows more or less the cyclical pattern we've seen through that period. When we then move on to the 2021-2022 model, it also includes long-range transmission and seasonal waves, but only in the epidemic element. And we see here how the simulations can also can simulate the pattern that we saw with actual outbreaks during the summer period. However, then we looked at recent data. This modeling exercise was from 2016 to 22. And if we look at the most recent data, we're starting to see a different pattern yet again. So now we're actually starting to see maybe it's becoming a little bit cyclical again, although we do have small amounts of detections that seem to circulate. So HPAI seems to circulate in wild birds year-round in Europe, but at very low levels. This shift could be due to various factors. It could be flock immunity in certain bird species. It could be changing in the timing of behavior or migration. It could also be changes in the composition of circulating HPAI-V genotypes, or that could have something to do with detection and reporting, which I will also discuss a little later. So, because the pattern changed yet again, we recalibrated our model with only newer data. And here we find we only have one seasonal wave both in the epidemic and the endemic element, and we see how the simulations can actually simulate the patterns we are seeing now. So we are seeing different patterns, and from now on, we have actually made this homepage where you can go in and look at this model. You can pick what country you're interested in. It'll look something like that, the Enigma HPAI model. You can go in and look for forecasting, pick the country you're interested or Europe as a whole. We only forecast 4 weeks ahead because, as everyone knows, the longer we forecast in time, the higher the uncertainty. You can also look at model fit and how each element in the model, whether the transmission is deemed to be endemic or epidemic between countries or within countries, that actually shows the size of each element. And you can also go in and look at a description of the model with links to the papers that are behind this model. So we saw cyclical seasonality in the model from 16 to 21, and then we saw more or less constant endemic contribution in 2021 to 2022, and now it seems like we're back to the cyclical part. So for the model we can that this web page is based on, we actually now only go 1.5 years back because we need enough data to run the model, but we don't want to go too far back because the pattern seems to be changing over time, and so we keep recalibrating the model. I did some work. I went to Australia and did some work together with Michael Ward from the University of Sydney, and we decided that maybe it would be interesting to expand this model to Asia. And we looked again at Warvahis data for Asia and also Empress I from FAO, because it seems like a lot of Asian countries report more to FAO than they do to Warvahis. Turns out we had a lot of sparse data in some countries, and we ended up with having only enough data for South Korea and Japan. So we created a model for South Korea and Japan, and we divided both into regions based on geography and partly on local division within each country. And we chose data from late 2020 to 24. And here we again we have the map to our left, where we can see how some of the regions within South Korea seem to have a high number of detections relative to their area size compared to Japan. And if we look at the detections over time on the graph here to our right, we can see that unlike Europe, this is highly seasonal, the detections that are going on. We see nothing during the summertime. We see detections during the autumn and spring, like we saw in the early years in Europe, which is quite interesting. We did the same thing we did with the European model. We used H5 subtypes. We combined domestic and wild birds. And then we looked at the weekly number of detection for each region. We used region areas offsets and wetland and coastline as covariates, and we added seasonal waves and different kind of transmission, short versus long range, and we then ran multiple combination and picked the best model for that could predict and forecast these detection and the seasonality. And if we look at the simulation, again, this is the fan plot with 1% and 99% quantiles, with the white line being the mean, and the open circles being the actual detections. We see how this model actually predicts really well. But of course, when we have this pattern that is consistent, it's easier to model. The data for Europe makes it much harder to model because it changes over time. This model had one seasonal wave, both in the epidemic and endemic component, and took into account long-range transmission. So this modeling work made us believe that it was actually possible to use available data from surrounding country or regions to look at risk assessment and forecasting what's going on weeks ahead. We found a fair congruence with the reported data for all countries and regions over time. And we found that seasonality is more distinct in East Asia and in Europe. And we actually decided to talk to a lot of bird experts to find out what is going on. And what we believe is it could just be that the virus never had the opportunity to spread quickly in dense colonies like tern, gulls, and cormorants that it did in Europe. That hasn't happened in East Asia. So maybe that could explain some of the patterns that we see. We also know that a lot of the large goose and swan species that overwinter in Japan and Korea, they breed in the Arctic regions of Russia, and they actually never come into direct contact with those from Europe. So it could just be by pure luck that they are not seeing the pattern that we're seeing in Europe, and that could be again flock immunity because we had a lot of outbreaks. It could be depletion of some wild bird population that are susceptible to HPAI, or decreased reporting or detections. All in all, what we saw for Europe, that over the years, the endemic component actually increased. So it seems what we suspect is that HPAIV is circulating in wild birds year round and has an endemic component, and this model seems to support that, whereas in East Asia, it has been constant over time. Of course, there are caveats to modeling this kind of data because, as I said, the modeling framework is very data driven. So it can only be as good as the quality of the data we receive. There could be some reporting bias. There could be some countries that report less than others. There could be different surveillance methods or even efforts. Also detection bias. Maybe some countries use different passive surveillance, active surveillance. And also, disease absence is a really good thing, of course, and we would be happy that, but it's not so good for modeling. If we have a lot of zeros in our data, the model goes really weak and it doesn't get as much power as it is data-driven. So it's important to know the limitations of this. Also, you can always improve. Our next step is trying to look at maybe simple genotypes, model separately for those, model separately for some of the bird species. We want to include bird migration routes. We just haven't quite decided yet how to quantify this. And we also know that bird behavior, bird migration is dependent on a lot of climatic factors, wind, water, and temperatures that has been found in earlier studies also having an effect on outbreaks. So we would like to include that in the model as well. And with that, I would like to thank you for listening to me, and I'll be happy to take, I don't know if we take questions now or if we take at the end of this webinar. Thank you very much.
Thank you very much, Lene. This was an amazing presentation. It was very informative. So some of the problems that you mentioned that we are experiencing as well, but the patterns that you mentioned in different regions. So obviously we have heavily focused recently on Canada, but the patterns that you mentioned, that they're quite insightful. So maybe we should also have another look at your paper and understand some of the risk factors that you mentioned that may contribute in some regions to be a little bit more consistent and predictable versus the ones that are not, especially in Europe, because I think our pattern could be similar to yours.
Yeah.
So
that makes it hard to predict. Yes, you have to keep an eye out on the data and see how it changes, and then you change the modeling accordingly. Yes.
Yeah, so that's true. So one quick question on my side, and we go to Jose. Do you think, so you mentioned you have to constantly modify the model, the models that you're using. Do you think machine learning, some of the more I mean, that's a tough one because we don't know either. Do you think because they look at the context a little bit more effectively, do you think we have enough data to just say machine learning in some cases could be a little bit more powerful to look at more in-depth patterns, or no, we are not there yet, or we may never get there?
You might be able to, definitely, but I would suspect that because the pattern changes so much, if we use machine learning, you should not go all the way back to 16. You would have to, like we do here, you would have to look at the newest data from the newest patterns, because otherwise the machine learning might go completely off track and off the rail. But machine learning, I'm sure you can use that as well. Yes.
Maybe in the future, if you have a lot more consistent and high quality data. So thank you very much for that. So we will take questions. Yeah. So at the end. So Jose, I will go with the introduction. So Dr. José González is a veterinary epidemiologist whose research interest is studying transmission and control of infectious diseases. He's currently leading the epidemiology and risk assessment group of Wageningen Bioveterinary Research. His group developed the models and performed the analysis to support the EFSA opinions on assessment of vaccine efficiency and vaccination strategies, and the opinion on surveillance of vaccinated poultry populations. So Jose is also quite, he's a celebrity from what I've heard in Europe and from my colleagues also in Canada. So we are very delighted to have both of you, Jose and Lene, here to present your work. Please take the floor.
Perfect, Rosita. Thank you very much. Well, I feel honored, and thanks for inviting me to be part of this symposium. Well, now that Lene gave a bit of a regional and global approach, and I'm gonna zoom in a bit into the Netherlands and touch on a lot of the topics and factors that Lene mentioned that are limitations when we are modeling, that we are also exploring, but now what I'm presenting here is the work we are doing in a higher resolution, but only for the Netherlands. And still, it becomes very challenging. So what I'm going to be presenting is all the different studies we've been doing, trying to understand all these drivers of infection in both the wild birds and poultry, and how we've been exploring the use of machine learning models to try to develop some risk maps for geographical hotspots or spatiotemporal hotspots for both type of populations. Okay. Well, this is my institute. I'm part of Wageningen Bioveterinary Research. We are in a place, the name is Lelystad in the Netherlands, around here. And here we have the institute is a reference lab for the Netherlands for notifiable diseases. And we are also a FAO reference center for veterinary epidemiology. We have a team of 14 epidemiologists among mathematicians, physicians, biologists, veterinarians, animal scientists in the group. Well, this is just a very rough and crude overview of the situation when it comes to avian influenza and how it's moving among different species. Well, here I have the pig because concerning, but it's to represent mammals. Don't focus on that. But well, the whole situation is going from what is the risk in wild birds across all the way toward humans. That's a work also we are doing a more in a more broad sense, but today I will focus only on the wild birds and poultry. And when we try to look at the risk of avian influenza in poultry, what we are trying to understand quite well is this interface. Which are the drivers that are leading to us, or that are leading to us this spillover from influenza from the wild bird population to poultry, this interface. So what I'm presenting now is the work we've been doing, trying to identify all these different risk factors that lead to introduction into poultry, and then how we use this understanding to try to develop some risk maps, in this case for poultry first. And well, we first started, we looked at all the different, we used data from all the different outbreaks we had since in the last 5 years, since 2020. Since 2018 to 22, actually, sorry, that period, and I will be showing results from that period. And we use just classic statistics, a simple logistic regression, and we look at all the data. We went deep and look at different variables around farm level, but let's start with looking at the poultry type, and some of the results what we found there is that when we use as reference the layers, commercial layers, and actually also breeders, because we didn't find any difference between layers and breeders, so I'm putting them both together here as a reference. We saw that chicken broilers have 5 times lower risk. These are odd ratios than commercial layers or breeders. But we also saw that turkeys and ducks have a significant higher risk, almost 9 and 5 times higher than the risk of introduction. This is introduction of in relation to poultry. But now, another point that we were very interested in is see this interface, which variables lead to this introduction or protect against this interaction. And this had to do a lot with the land use. And what we saw there is that whenever that around the barn, the poultry barn in the farm, the higher the area of grass, agricultural grass around the barn, the higher the risk of introduction of influenza. We also saw that the distance, the shorter the barn was to a water body, and the wider or the bigger was this water body, the higher the risk of an introduction of avian influenza. Interestingly also was that we look at the higher the area of the more trees there were around the barn, the poultry barn in the farm, that was actually a protective factor. So what the trees were doing were somehow reducing the risk or the probability of introduction of avian influenza into the poultry barn. So in summary, well, we also look at the many different wild bird species. We have the wild bird density in the Netherlands and in Denmark, by the way, is really large. We get a lot of migratory wild birds coming in our direction for wintering. So we have a high the richness. The species richness is very high, and also abundance. So we look at many different species, and we look at the association between the population density and the risk of introduction, or at least the probability of introduction we have had. Sorry, these names are all in Dutch, but a lot of these wild birds that had whose density had some association with the probability of infection in poultry, where a lot of those were mostly from the Anatidae family, I think. And this is, I think, a summary for you to see of all the risk factors we found. As you can see here, this is a poultry barn. It's all closed, poultry area inside. But this was one where we had an outbreak, for example. And as I saw, statistically, the more grass you have around, and the nearby you are to by water, the higher the risk, because, well, this attracts a lot of wild birds, as you can see here. And with wild birds, those are the primary host of avian influenza. You increase the risk of introduction. And what we did, we used all this. We used this data, or what we learned from this, and we started extracting much more data at high resolution. So we went down to grids of 1 hectare grids. And we collected around 96 variables for each grid in the Netherlands, and around land use and land cover. And we also collected the data from all the relevant wild birds we identified in what I showed before that we thought were more relevant. And we combined all this data and tried to use machine learning models to risk map. Well, we tried different types, and I think the best model we got was a random forest model. And with that, we reaching accuracy of around 90%. And with that, this was we could build this map where we could identify the high risk, these more reddish oranges areas where there is a higher risk of introduction if we were to have, or do we have poultry farms there. Now, when it comes to wild birds, yet this is really more challenging, and this is because, well, there's a lot of bias in the data. If we do our best in surveillance and looking also and detecting avian influenza in wild birds, but still there's a lot of bias in what we get. There is a bias in the level of infection in wild birds and the number of species we have. And as Lene said, just mentioned, there's a lot of variation around it there from year to year, and that has to do a lot with the virus evolution, because we get many different genotypes every year in every season, and we get new species being affected, or some species being affected much more in some years than in other years. I will show a bit more about that. And this, of course, affects also the temporal and the geographical distribution of influenza in wild birds, depending how it's affecting the different species and which new species are becoming infected. However, besides all these biases, we have some data and we can do something with it. But I will go a bit deeper in what are the issues we have when it comes to the data. we go collecting. For example, this is how more or less how the passive surveillance system in the Netherlands work. In Europe and in the Netherlands and in Europe, passive surveillance is based on reporting mortality in wild birds and submitting some of these mortalities to the lab for diagnosis. We have many different institutions, organization, volunteers doing the reporting and submission to the lab. Mostly the key ones of those are this SOFON, this Ornithological Institute, and this is the Dutch Wildlife Center. Usually all the mortalities are reported here. Most of the mortalities reported here, and from here the samples will come to our lab. But we have also all the institutions or group working on bird ringing and monitoring the movement. And what usually they do, they will send samples when they are ringing and take samples or detect or find dead wild birds. They will send it to Erasmus. They are dealing with the active surveillance and then they will do the diagnostics. But there are many other initiatives that they do report mortalities, but those samples are not being submitted. So this and therefore we have no testing on those samples, on those mortalities reported, and this brings a bias in our detection capacity. But that's all. But that's all. Just diagnostics and our diagnostic coverage is not the only issue we have to deal with. The other one is the reporting, because the reporting by itself, finding a dead wild bird, that in itself is a challenge. And then reporting that also has limitations. And getting a sample from it and send it to the lab, it reduces even the probability of detecting something. This is an example I'm giving in case of mute swans. Mute swans are the species where I think we have the best sensitivity to see if there's a mute swan dead, the likelihood that somebody will see it is high and report it. And that's why we see a lot of mute swans reported and infected in Europe, for example. And what I want to bring to your attention here, for example, in the middle is the density, the population density of mute swans. Here are the reportings that are done. This is in a peaceful year when we didn't have big epidemic of flu. This 2019. I will show you a figure about that in the next slide. But what you can see here's a lot of reporting is going on here. This in the main city around Amsterdam and that region. There are a lot of people and there's a lot of reporting, easy to see. And you will see the reporting of mortality here. When you look at the densities, we don't have that many mute swans there. Compared to these regions here that are dark blue, we don't have any reporting of mortality there, or here in the upper part. So this already is bringing a bias in how the mortality is being reported, what mortality we are detecting, and how much we are missing. So there's not a good and a representative coverage of when we are trying to monitor mortality. And when this increase, when we see an increase in mortality, and we have after correcting for all this bias, we can see a bit, we improve a bit, as you can see here. But the sensitivities of detection and actually all the way to diagnosis are very low. I think this is our estimate. We're still working on this, but we are around 5%. Evolution, yeah, as was mentioned, the virus evolves and then it changes. Here's just an example of a few species, more Anitidae, that I chose to show. We have many more. In others, you don't see any difference in mortality along the years. But I would like you to bring your attention to these two. An epidemic year or an influenza year in Europe goes from October to September. And each here, what I'm showing in the x-axis, you will hear is going from the influenza year of 16-17, October to September, all the way to 21-22, which was the year where we have the biggest epidemic, an H5N1 in Europe so far. But in 16-17, we have a big one, well, the first big one at the time, and it really affected the SMINT. Oh, sorry, SMINT is now I have a Widgeon. I'm mixing Dutch with English now. Sorry, the SMINTs are the Eurasian widgeons, and it really affected widgeons. And we had huge mortalities here. Here is around 1,500 if you cannot see the number. But in other species we didn't have that marked mortality. maybe a bit here in the common shell duck, but look at the barnacle goose. We had almost no reports of mortality in these years in barnacle goose. But in 21-22, we have huge mortalities, massive mortalities in this species. Now, I bring your attention to the common teal. In 1819, we had, again, an epidemic going on, mostly in wild birds. And here we could see a relative increase in the mortality reports in common teal. Or look at the Brent goose. Here there was a difference between 2021 and 21-22. This was an H5N8. This was an H5N1. So all this has changed how the picture we have on the outbreaks and the risk and the seasonalities, as Lene showed, behave, and it's very challenging. And this only for a small set of species that I'm showing. But something that I will bring your attention is here, using orange. This is the 1920, was the lowest we had in all this period. And also in mallards. In mallards, for example, we hardly see any change in increased difference in mortality. Well, in 21-22 a bit more, but in general it's stable. But in 1919 was quite low. Also, we would use mallards as reference. So when we try to model this, we try to develop a spatiotemporal model for wild birds, and they try to map the Netherlands. And I will say why we wanted to do this. Yeah, we're thinking, how are we going to deal with all these different changes we have along the years in the impact of the different viruses on the wild birds, and how these behave so differently among wild birds. I show the ones where you see mortality. In others, you don't see anything, and many other species you don't even see any mortality is not reported because they don't, especially the smaller ones. So we were brainstorming about it, and we came with an idea. We said, let's do a case crossover design. Let's use a case crossover design. And what is a case crossover design? How we approach this? What we did is this 2019, a year where we thought there were hardly no avian influenza, of the prevalence was really, really low. So we used as a control, and we took all the cases we have in 18 and 20. And how we approach this, for every single case of influenza we had with a confirmed detection of avian influenza, regardless of the species, we look at 19 at the same date and the same location. And we look at all the mortality. So we didn't look at any species. We sum up all the wild bird species and we sum the mortalities we saw in around that location at that time. We make a window, a spatiotemporal window, and we sum up all the mortalities that were reported around that time in any day in this case. And we did the same for the same pace and location and a temporal window that we defined in 2019. So the location and the time were the same control and case. And we use Bayesian models where we did with this spatiotemporal rate, which I said was the location and a time window around that location in 220, which was the case, and then again in the same location, but in 2019, we look at different other variables, and we started the modeling. We have like 24 different models. We did all the cross-validation, the folding in these models. We build the models, and these are the results of the validation data set, and then they were not perfect. I think the best we got was a bit higher than 80% areas under the curve, 80% areas under the curve. But with our best model, we could get these risk maps per month. This starting in October, you go all the way to September, where we started defining which areas where we think there's a increased risk. And why we need that? Because here we have what we call to inform housing orders. In the periods where we have a higher risk of avian influenza, then we have like 50% of our layer population, commercial layers, they have free range access. And if they are outside, the risk is even higher for them to become infected. So in these periods, if they are in these regions, so what we want to say is, in these periods and in these regions in the country or in these months, it's better to keep the chickens indoors. And also we want to use this to start improving our surveillance. So in summary, what we have done so far in poultry, what we found is that the land use and the poultry type are key determinants of risk. So then we are also trying to make getting areas with more trees and making some measures in that direction. Also kind of replanning farm locations and all that based on this information. What about wild birds? Well, the challenge is still how we generate the data we have, but we are trying to improve that so that we can improve also model accuracy. We are working on that. But despite these limitations, we could use the data. We are trying to improve this, and we can be used this for housing orders. I mean, to try to optimize surveillance. The ongoing and future work we are doing, where in case of poultry, we are looking at biosecurity. So we have looked what is going on around the farm. Now we are trying to look at in the farm. We have cameras monitoring, video cameras monitoring the biosecurity in some farms that are participating, and we are trying to understand more all the mechanisms of introduction, looking at air inlets. Well, we are going into higher resolution in this sense, working a lot with vaccine efficacy and developing models to predict the duration of protection of a vaccine based on humoral responses, protection against transmission. And in case of the wild birds, well, we are working a lot in trying to estimate the true prevalence in different species or species of concern, trying to now to link the genotype of the viruses we have that emerge in time and space every year to the phenotype, trying to link these different genotypes to mortality increases or mass mortality events within different wild bird species, and improve surveillance. We want to go towards risk-based surveillance and improve our diagnostic coverage. And we are validating pen-site diagnostics to be applied in wild birds to try to improve the diagnostic coverage, which is also an issue that we have detected. And of course, all that is that I have presented is done by. I need to give credit to people that are cleverer than me, and are all these guys who managed to generate all these results so far. And with that, thank you. If you have any question.
Okay, thank you very much, Jose. The presentation was very insightful, very interesting findings, and you have a large team that are working on this different aspect of avian influenza, and I think this is quite amazing because you can eventually bring all that insights together to something that would be way more comprehensive. So I will start with asking few of the questions that are on the chat, and then I'll pass it on to Dr. Buthu to take over. So I think Lene answered some of the previous questions. I'll start with Corey's question regarding, have you used machine learning in any of the modelings that you've done? And which one did you pick, or how you picked those machine learning? Did you use machine learning, or the person who used machine learning would you be able to speak on that, or?
I think Jose did. I did not. I used statistical models, but you were talking about random forest models, Jose.
Yeah, that's for Jose. Yeah.
Yeah.
Yes, we use. Actually, we are also using to try to come with global predictions. So we are using quite a lot of machine learning models. The one I showed now was the one that behaved the best was a random forest model, but we tried also neural networks, and we've been trying other models too.
Okay. Yeah. So so just wanted to with my experience, with machine learning, when you have high quality data, there are a number of factors that can help you select the machine learning method. How big is your data set, and then what the format of the data set? Does it need pre-processing? Because the new machine learning methods, they don't need pre-processing as much as they used to, but you need to have a large data set. Generally speaking, random forest, which is an ensemble, is quite powerful. But again, you have to try a number of them and then select the best ones, given so there isn't one machine learning method that would fit all the problems. So it depends on the number of factors. But the other question from Mina, she's asking why, this is for Jose, I believe, why did you choose the grid size versus the common or the most commonly used one that is 5 kilometer? Generally, yeah.
Well, because this was for the Netherlands, and there we can go down to 1 hectare. So we wanted to increase the resolution, and just in place we had. When we look at it, we could look actually that the area of grass and the area of water around your farm was more informative than the Wahlberg density, because the Wahlberg density was a 5 times 5 kilometer grid. And what you get there thing is, within the Netherlands is very small. So within 5 times 5 kilometer grid, what you have is farm A here, and let's say 1,000 meters away, you have farm B. Oh, okay. And if you go in such a large grid, you won't find a difference between what's the risk or what is predicting introduction in farm A versus that farm B, because you don't have that level of resolution. When we go to the hectare, we know that farm B has less risk than farm A because of this high resolution we went down.
Okay, excellent. So, Lene, do you have any, also, both of you, how to select the grid size? Canada is quite big. So if we go with the resolution that Jose used, it's our data would be huge.
Well, Well, it depends on the data you have. What is the resolution of the data you have? And also, the smaller the grid, the more zeros you get, right? So for a model like the one I was using, if I go, so we decided on countries in Europe, also because if we go a lot smaller, then we'll have a lot of zeros all of a sudden, and then it makes, so it really depends on the quality of your data and also variables you're looking at what resolution are you able to get these variables.
No, absolutely.
For we are trying some global models. There we are going 5 times 5 and even 10 by 10 kilometers, because you cannot get high quality data. We can, so that's why we went into that level.
Yeah. So would 50 by 50 make sense, or is it too large, you think?
At the global, that will be the Netherlands. For us. The global, I think that's a bit too large.
Yeah, that's interesting. And also, Mina is asking, where is it? How did you define negative points in your random forest model? You mean negative points in the data? Did you have any specific constraints? Yes.
Yes, because I get in the random forest for poultry, that was a case control approach. So the cases were all the grids, the 1 hectare grid where we have a case farm. Introduction, no transmission. So we removed anything that had to do with farm transmission. They were all primary introductions. And then we did a run. We selected randomly, matched by poultry type. We know that poultry type has an influence, so we wanted to exclude the poultry type out of the random forest to do the prediction. So we matched by poultry type first, and then we selected randomly from our selection of negative farms that never had an outbreak, because we are very confident of it, and within a distance. So we put a limit of distance. I think it had to be at least 10 kilometers from the case, and we selected 4 controls. We did 1 times 4 controls for each case, because we needed also to increase the power. And we did, I think we did like 10 different sets of controls to double check that there was not some bias in our control random selection. And then we ran all the random forests, and then we put all those together, and we made our prediction.
Okay, excellent. Thank you very much. And Lene, do you want to add to this?
No.
Okay. So we have a question from Yang Fan from University of Copenhagen. I'm curious about the predicted outcome in your random forest model. Is it a binary variable or a count variable? I think you have answered this, didn't you?
Yeah. No, it's a probability.
Oh, it's a probability. Okay. The next question by Ali. I was wondering, are the risk factors for broiler breeders and layer breeders considered similar to those of commercial layers, and or are these important? Are these even important differences?
Well, in our case for the Netherlands, we didn't find any difference between the breeders, a significant difference between the breeders and the layers. And I should also note that all the data, when we had all the outbreaks in this period, we had housing orders. That means that all our free-range layers, like almost 50% of our population, farm population, are free of commercial layers have free-range access. They are compulsory. They are kept indoors in this influenza high-risk period. So we didn't find differences between the breeders and the layers, which was we were surprised by it, and that's why now we are monitoring with cameras, and we look at the inlets and try to see also airborne virus, and we are going into all those small details.
Okay, that's amazing. Very impressive. So I'm going to pass it on to Dr. Nitish Buthu from here, because I have to attend another meeting that I can't be late. But thank you very much for the time you spent to present and for sharing the amazing research that you do. Thank you very much.
Welcome.
Thanks, Rosita.
Thank you.
Okay, thank you very much. So continuing this discussion, if you were to, because you both looked at the general country level and maybe more in some areas at regional level, would you be able to decipher the difference between what are birds that are non-migratory birds, but more birds that are wild birds that are residing in these areas? The difference in terms of HPI levels between them and compared to migratory birds, and whether you see the same pattern of high infection, low infection. I think Jose, you kind of mentioned a little bit about looking at differences between the same areas. So I'm just wondering whether there's a way to decipher the difference between the two of them, and whether that is something that could be of interest for the future as we look at increase immunity or decrease immunity in terms of the wild bird population itself, in terms of trying to tackle HPI spread.
Lena, do you have?
Yeah, well, it's very interesting. Like the modeling framework I presented, we don't discern wild bird species. We don't even discern between wild and domestic birds. But it's definitely something we have been talking about, seeing if we can create different models for different species. We know, and I know Yang Fang, I work with her, who has been asking questions. She is looking at different wild bird species within Denmark, because we've been looking at some of the species that are actually where we find the most cases. And so we think they might be representative. And so we included them in her very fine-scaled model. So there is definitely a difference. That's what we find. We also find that some species may be more immune than others, but this would also need, I think it would need further experiments, actually, Jose, that doing something to test the wild birds for immunity in the future. Yes.
Yeah, well, if I complement to it, yeah, we are looking at a bit more in detail now to the species level, as mentioned, that you have this variation, and sometimes a lot is focused on mute one, for example, because in Europe it is reported and detected a lot. But a lot of things, I have the impression, I think when we look in detail there, it has to do just because you see it, and you're more likely to find it, and because it is big. And we have other species that might bring much more information, but we need to improve the surveillance in that direction. And now, when we look at the seasonality, as you asked, a lot of these species, like for example, I think like mallards, you have also resident populations, and you have the ones that are migrating. Usually, the migrating are dominant, are much more than what stays in our countries, in the Denmark or the Netherlands. And with that, you also see a drop usually in the prevalence. That's something we saw also with low pathogenic avian influenza. We also learned that, and I think it's something has to do also with whenever there's a new wave of migration coming from Eurasia. So you have much more mixing also between different populations, and there are new younger populations coming in, and that is bringing a lot of exchange of viral exchange, and that brings these different waves we see.
Yeah, that's it. Because here in Canada right now is ducks and geese season. So you see little ducklings hatching, or their second year now, but they may not have been exposed so much to HPAI as compared to their parents, for example. And as they start migrating more north and south, they will start getting exposed to them. So to these viruses that are circulating. So that would be really interesting to see generational gaps in terms of how populations of various migratory birds are impacted by HPAI and how it affects its evolution itself. So I think that would be really interesting to see more work from you guys about how to really track these things and making more predictions about this. The other part is because Europe has a very big emphasis on rewilding the general areas around farms, around cities, and so on. And a lot of your data also is about prediction of presence of HPI in various areas that are either low population or high population density in terms of human population. So is this something that you guys have looked a bit more closely in terms of whether there are certain associations between where there's high density populations of humans and in comparison to high farm densities, or how non-farm, non-rural, but more forested areas, seeing the presence for HPAI. So I think, Lene, you showed that in your Japan modeling, there were differences in various in frequency of HPAI, but whether you guys were able to go maybe further into looking at what are the areas within that. So temperate climate, forested climates, and so on.
Yes, but that's what we're planning to do now. We were just looking spatially how it, that was the main thing, but we would like to add some more variables. So definitely some climate variables and also some more landscape variables. We were focusing on wetlands and coastline because we know, especially for Denmark, that's where all the migrating birds aggregate each autumn and spring. So yes, and we regarding population density, I actually did a previous study I did. We looked at passive surveillance of HPAI in Denmark, and we tested a lot of things regarding as to this, because it's whether it's biased or not, depending on closeness to cities, because it's dependent on the public finding these birds and reporting them. So the closer you are to a city, the closer you are to a road, public beaches, that actually had an effect as to where you find the birds. And again, as José said, when they're big birds and they're like raptors that people are fascinated by, they're more likely to report them than a dead sparrow. So there's the data we have is inherently biased when it's based on detection.
So is there a way that you think in terms of communicating? So right now it's the summer season. So in terms of when people are going out, in terms of communicating, either with infographics or just in terms of what we should be looking for so that we can improve the data quality itself. So is it something that we should be doing? Is it something that the government or generally we should tell the public that you should be doing this? So because we spend a lot of time telling people avoid certain things. So because data is quite important for predictive models. So what is your insight into this two-sided conundrum, I would say?
It depends a lot on your government, because in Denmark, it's we actually have meetings. I'm part of the expert HPAI meeting together with the Ministry of Veterinary Animal Diseases, and we or the Food and Administration, and together with the EFSA's bird flu radar and our because our model is publicly available on that webpage I showed you. We look at forecasting, and they use that to determine whether or not that, but that's for farmers, whether to keep the birds indoor or not. But as for asking the public what they should do, depends on the government and the guidelines. And I know, for example, in Denmark, if they find HPAI in an area, then if someone reports a bird in the same area within a week or so, they probably will not test it because they know it's there. So then we're missing some cases, but that depends on the rules and legislation in each country, I think.
Now we have similar issues with, as Lene mentioned, regarding the reporting and testing of wild birds, for example. But now we are trying to move towards making a bit more risk-based and more coordinated, and that comes also the use of the pen site testing to improve our coverage in terms of diagnostics. So the more we learn, I think we go adjusting also these processes.
We also, in Canada, we have a certain discussions around how CFIA and also how we should be handling control zones here. So yeah, when HPI is detected in a certain area, control zones can not only impact infected poultry production system, but also non-infected poultry production systems. So being able to differentiate between the two is quite important. I think it ends up putting everything in one category as being infected. And that can maybe skew also the prevalence by saying there might be a higher prevalence of certain presence of certain pathogens in certain areas more so than other areas. Well, it might not be entirely in that around. Maybe it might be in 2 weeks from now or a month from now, but we don't know for sure how it's moving. So yeah, that would be really good to actually discern between these two. Yeah, and just last thoughts for today, as in thank you for both of your presentations. If you had like a golden wand and you would want something as a best wish, because this is about discussion about how to track HPI and making predictions much better, and also making decision systems much better, not only in terms of models, but also for governments as well, because we all talk to government industries about how to handle HPI. So what would be your golden wand moment, like a fairy? What would you wish for?
More streamlined, for modeling purposes, more streamlined and similar efforts from all countries, because that is something we do not know, the detection bias or even the efforts done by each country. That would help immensely. And also,
yourself, Jose?
Yeah.
Well, I would wish for this to be back like it was before 2014, but since that's not possible, I actually Lene read my mind. was in the same direction, and actually we put a kind of a small proposal to try to standardize our modeling approaches and get together and then data generation with the team of Lene also and other colleagues in Europe. Hopefully we get it.
Yeah.
Well, I would like to thank you both for your presentations. It was really great. Really a lot of insights. I think at today's talk we also had many people from industry and from government as well here in Canada, and a few people from Europe. Also understand that today is a bank holiday in many parts of the world, so many people could not attend. But also knowing that this is recorded and it's available online, so people will watch it again at some point. But in any case, I would like to thank you all for attending today's seminar. If you have any questions that we did not address, you can always email myself or contact the presenters directly, and we can hopefully get in touch. If you're interested about the work that they're doing as well, and you're interested in collaborating with them, please, by all means, do get in touch with them and see how best you can collaborate. Thank you very much, Lene, and thank you very much, Jose, for your talk today.
Thank you very much.
Bye, everyone.
Bye.
Thanks to you. Bye.